That was easy.
Alright, so I wanted to make this video for a very long time and I finally get the chance to make it. I want to answer here, why do we actually study theoretical computer science? Well, aren't all the applications of computer science completely practical? Why do we even care about theory? And a lot of people have been asking me this over the years, and I didn't have a really good answer until I started to think about it for a while, and this video is the result. So enjoy. I'm going to give you my top 10 reasons for why we study theory in computer science. So the first one is, does non-determinism lead to efficiency? And the answer in general is no. So if you don't know what this is, non-determinism means you have a way of guessing the solution almost instantly in some sense. Like, you know the way to the solution instead of trying to do some additional computation to try to figure out what the solution is. And the answer is no, in general. So, as an example for what you learn in the class, we talk about non-deterministic finite automata and deterministic finite automata too. So it turns out that they're equivalent in power because we can convert any NFA into an equivalent DFA. So the non-deterministic thing is equivalent to the deterministic one in the sense that they compute the same functions, they have the same languages, but the problem is that if you look at a particular language, in general, the minimum DFA in terms of the number of states that it has for that language is going to be way larger than the number of states for the non-deterministic one for L. And it could actually be exponentially larger, which is really, really annoying. So it's not necessarily efficient in the sense that you were able to compute the actual DFA, but the fact that it exists, that is what's important to realize, that there's some kind of relationship between what can actually be computed, but also how efficient you can actually compute the thing. So that's the first reason. The second reason along these lines is about what can actually be computed versus how they're actually computed. And I'll use the same example here. So I have a little DFA and NFA right here. And of course, they're equivalent in power, as we've already mentioned. But the way that they're actually computed is different. So the DFA, of course, has to read the characters one at a time, which means that it does one transition at a time. The NFA does the same thing too, but the DFA makes a deterministic choice in that it only has exactly one choice it could ever make at any point. And the NFA, on the other hand, has a bunch of choices that it can make. And how non-determinism helps us here is it guesses the solution correctly if there is such a solution. If there's no way to get to a final state in this case, then that means that it'll just make any choice. But if there is a way to get to the final state, let's say that guy right there, then it will make some set of choices that will eventually lead to that particular state here. As long as it reads the whole input, of course. But that's just a detail that I'm going to gloss over. The important thing to realize is that these two devices, even though that they are equivalent power, compute things differently. And so there's not necessarily a canonical way of computing something. There's maybe a canonical representation of something, but not in terms of the actual computation. So that's the second reason. The third reason is that there are different models that are all equivalent for different types of problems that we care about. So if our problem happens to be a regular language, then we have a bunch of choices as to what to actually use for that particular problem. So maybe a machine is actually really efficient, or maybe using a grammar is efficient, or using a regular expression is. So if you want to parse emails on a particular website, you would want to represent that in the code as a regular expression. And on the back end, because all three of these red models are equivalent, we can convert the regex into an equivalent DFA and do the computation of whether we should accept or not in the DFA, because regexes don't really have a notion of computation, but they are equivalent nonetheless. And the same thing is true for different models. So I have deterministic context-free, context-sensitive, which is usually not taught in intro theory, but I'm including it anyway, and recognizable. So here, the deterministic context-free are the blue guys, And all of them are equivalent to each other, so there's a procedure to convert from one to another. The green ones are equivalent, and the yellow ones are equivalent, and the pink ones are equivalent. So you can always convert from one to the other. And depending on the problem that you're interested in, you can always just switch from one to the other. And so that is the third reason. The fourth reason is that for some models that there is a canonical representation for the problem that you're interested in. So one thing that you'll prove, possibly if you're lucky, is that for a particular regular language, there's always a unique minimal DFA. So if you have a DFA for some language, you can always minimize it, and it always will give the same answer, no matter what the DFA is for that language, which is pretty bizarre. But it actually is true, and you use something called the Myhill-Nerode equivalence relation to be able to prove that. But if we talk about the equivalent models in terms of what they compute to DFAs, which are the NFA and regexes, and actually literally any other model that is usually studied in this area, there's no unique minimal representation of that thing. So I have an NFA in both of these. They compute exactly the same thing, and they are both minimal in terms of number of states, but they're not the same, because the start state right here has a single A, single B, single C coming out of it, whereas up here it has two transitions for an A and two transitions for B, two transitions for C. And it turns out that these have exactly the same language, but they're both minimal, but they're not identical to each other. So the fact that we have a DFA that is unique in minimal is always a really nice thing to have. And it actually turns out to be quite useful in some circumstances. If you know for a fact that this thing is the minimal DFA, now you know some basic properties about it, and then you can start doing other things. So that is the fourth reason. The fifth reason is that we can handle infinity really easily. So you may think, okay, these are finite automata. You only have a finite number of states, and so you can only do a finite amount of work, which is kind of true, but not really. In the sense that there's only a finite number of states, but they represent an infinite set. So as an example, I have three down here, where we have, let's say a DFA, although it doesn't really matter, where we have a cycle in here. So if I read a long enough string, eventually I will repeat a state. And so I can keep going around that loop as many times as I like. The string that is being fed as input is finite, but the set that it comes from is infinite, because I can just go around this and collect the set of strings that it belongs to over and over and over. If you have a regular expression and have something non-trivial on the inside and put a star here, this says 0 or more times to repeat the stuff on the inside. So even though this is a finite size representation, it's representing an infinite size set. And in context-free grammars, if we have something like a variable is replaced with something non-trivial on either side here, with an s right here, which is the same variable, then we can go around that loop, so to speak, as many times as we want. And actually, some problems involving infinity are decidable, which is pretty crazy about certain properties of this DFA, for example. So maybe we can ask the question, does the DFA accept infinitely many strings? And you may think, oh, I have to check infinitely many strings to check whether or not it accepts infinitely many strings. But by using the properties of this thing, that it has some cycles in it, we can actually check that in a finite amount of time just by only checking up to a certain size. And after that particular point, we're guaranteed to have repeated a state. And so we will basically do the work that we've already done before. And so this question becomes decidable. There's a procedure to be able to compute whether a DFA accepts infinitely many strings, for example. And that is the fifth reason we can handle infinity really easily. The sixth reason is that we can use some helpful results to help prove other things. So the most famous of them, of course, is the pumping lemma. Lemma, if you don't know, just means a result to help prove other things. And the way that this helps us is that it helps us prove that some languages are not regular or not context-free. The main result we want to prove is that something is not regular, so that there's no DFA for it, for example. But the lemma helps us get to that point instead of having to redo the work every single time. The Myhill-Nerode equivalence relation by itself doesn't tell you a whole lot. It tells you some interesting things, but the consequence of it is that it helps us prove that the DFA representation, if we minimize it, is unique. And that is the important thing that we want to prove. In the context of Rice's theorem, in terms of undecidability, it helps us prove that many languages are undecidable. Again, the thing that we want to prove is that the languages are undecidable, but the thing that helps us get there is Rice's theorem. We do a little bit of work, well, okay, maybe a lot of work, but we do it one time to reduce the amount of work in proving other things a lot more. And if we look at closure properties, so maybe like some set of languages is closed under union and intersection and complement, if they're closed under those three things, like regular languages are, then you can solve the equivalence problem. So if I have two DFAs, I can check whether or not they really are the same DFA, in same language. Well, we could use this, but there's another proof that we can show that they're equivalent. We can show that if languages are closed under complement, and if we can solve certain problems, maybe about the emptiness problem, then we can solve what is called the universality problem, which is asking, does this thing accept everything? Because we can just do the closure under complement thing. So that is the sixth reason, to be able to help prove other things that we care about by considering certain properties of the models that we are investigating in the class. The seventh reason is that necessary is not equal to sufficient. So what does this mean? Necessary conditions just mean this condition has to be true no matter what happens. And sufficient means that if these conditions hold, then we can prove certain properties. So the pumping lemma, for example, it tells us that it only gives us necessary conditions for a language to not be regular. So if the language is regular, it has to satisfy these properties. But if you happen to have a language that's not regular, then it doesn't necessarily mean that it has or has not those same properties. If it's regular, it has those properties. But if it's not regular, that doesn't tell us anything about it. So we use that in the contrapositive. If it happens to not have those properties, then it couldn't have been regular. But that's kind of annoying, because if you want to prove a sufficiently hard language, you can't really use the pumping lemma. You may have to use some closure properties or something, but the tool that always works is Myhill-Nerode. And that gives us a necessary and sufficient condition. So if the language is regular, it has to have these properties. And if the language is not regular, it can't have those properties. So it's necessary and sufficient. And one thing that you should learn in this class is that if you have a necessary property, it doesn't necessarily mean that it is sufficient, and vice versa. So that's the seventh reason. The eighth reason is that these things have actual practical purpose in programming languages, as an example, among many, 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 many others, like robotics and systems and many others. But programming languages definitely. So regexes themselves are actually a programming language, because they're just a set of cases along with some recursive cases. And they form a programming language as a result. And you can solve a whole bunch of things with regexes, of course, to match emails or to match whether a password meets certain requirements. Many other things that you can do with regexes. But if you think about the regular expression conversion into NFAs, into DFAs, you can think of that as like a compiler, because what do compilers do? They take some source code and then do some kind of translation into some intermediate representation, and then maybe some lower level thing, and then maybe some optimization, and then we finally get to the machine code. This is kind of what it's doing, because regular expressions don't have any computation that you can do. You can describe regular expressions, but it doesn't tell you anything about whether this string is accepted by the thing, although that's not really true, but it's close enough. But when we convert down to here to say the NFA, well, you can do computation on an NFA, but it's not really computation, because you have to maintain what set of states that you're in. But if you do the conversion into the DFA, that's kind of like we now are in the very low representation, But we're not quite there yet because maybe we want to minimize this DFA, which corresponds to optimization in a compiler. Because maybe we have some really complicated program that is really, really slow, but if we perform some optimization, now it's really fast. So this is actually a pseudo compiler. It actually is a compiler, but it's not in the programming language that we're used to, but it's still a compiler nonetheless. It's translating from one high-level representation to a low one. If we talk about context-free grammars, those are used all over the place in the syntax of programming languages. So as an example, if you've ever had the experience, and I certainly have, of writing a program and it tells you you're missing a curly brace or a parenthesis, and you fix that, but then you get like 100 errors after that, what actually happens in the compilation process is that a context-free grammar is running on your source code and checking whether or not the parentheses are balanced or not. And you can do that with a context-free grammar. And if the context-free grammar fails, then it'll tell you, okay, you're messing it up right here. But if the context-free grammar passes, then we get into the semantics. So what do I mean by semantics? So for example, if we have int x is equal to 5, and then maybe I do print x right here, then this is totally fine. This is syntactically fine, assuming that it is the language that we care about. And it's semantically fine because we declare the variable right here. We say what its type is. We say what its value is. And then we use it after the fact. However, if we say we copy and paste this line up here, then what's going to happen is this declaration is semantically not fine anymore because the usage is before the actual declaration. But the syntax is okay because each individual line is fine. Remember, we're talking about context-free grammars. So the context doesn't matter with what a CFG can do. What a context-sensitive grammar, it will take into account the semantics of what's going on. And so the context-free sensitive grammar will take over and say, okay, yeah, there's something wrong that's going here. So that's the 8th reason. It's not just usage in programming languages, but usage as programming languages. The 9th reason is that we can understand that there's a very fine line between decidable problems and undecidable. Decidable problems just mean there's an algorithm for it, and undecidable means there's no algorithm. So as an example, regular languages have green check marks in all of these. They are all decidable. But context-free languages, they can do the acceptance problem and the emptiness problem, but can't do equivalence. So as an example, what I would like to do in programming language classes is the student submits a context-free grammar and I have a model solution and I want to check whether or not they're equivalent. This tells us that it's literally not possible to do. And there are actually some subsets of context-free languages that are still undecidable here. But the important thing is that this is not decidable and this is not decidable. And if we go up in power in terms of what we can actually do, what things we can compute, well, we get fewer things that are decidable. So for context-sensitive languages, we can do the acceptance problem, but we can't do virtually anything else. And for unrestricted languages, which correspond to Turing machines, which are programs essentially that we care about, that we program, effectively, there's nothing that is decidable. And so the question of what we actually do if we're stuck down here is the subject of the next one, but this is the 9th reason. So the 10th and final reason is what suitable limitations on Turing machines can we impose? So I'll give you a short story. A few years ago, I taught this class, and what I did was I taught it in reverse order. So what I did was I started with the Turing machine stuff, and after that point, when we saw that some things were undecidable, we said, what kinds of suitable restrictions can we enforce on this thing? So remember that a Turing machine is this one-way infinite tape like this, and we got a tape head that can read and write into a cell and move right and left. So the Turing machine, of course, can move right and left and blah, 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 change certain values and whatnot. But the problem with this is that a lot of problems are not decidable with Turing machines. So maybe you can enforce a restriction. Well, you can say, well, what if when we start over here, we can only move right instead of move left? Then it turns out that you're stuck in regular languages. What if we said, after a certain point, I'm going to cut you off. So after this point, you can't move past this point. So you can't allocate more cells. And that will lead you to context-sensitive languages. If you said, what I'm going to do is I'm only going to work from this end right here. So the only thing that I can change is this thing. So maybe I can delete something, but I can always append something. So maybe we'll get rid of that barrier. But what I can do is I can work right here, change that cell to something else. Maybe we'll say we're going to forget about it and then move left. And then maybe we'll say, okay, I want another cell and put one there. Then we're now in the land of context-free languages. So suitable restrictions on Turing machines can actually lead to all the things that we care about. And the thing that should be important for you to understand is that Turing machines actually need an unbounded tape because of the reason I just gave. So this leads to the really interesting question, well, is our universe actually just one big Turing machine? And that's actually a very hard question to answer, because if we have an unbounded amount of space, then we just basically proved that you can either always allocate more space in the literal sense of space, or the universe is infinite, and we don't know the answer to that. If the universe is finite, then effectively we just have a giant DFA on our hands because we can't allocate more cells and we can't have a super long input, longer than the number of atoms in the universe, if the universe is finite. So hopefully that was interesting. Leave comments about these 10 reasons into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.
That was easy. That was easy. That was easy.